Jnanam Paramam Dhyayam. Knowledge is supreme.
Let's begin this tutorial. It is a tutorial with variety of problems based on finding the energy and wave function of two identical particles which are non-interacting, and in line we have problems on the orbital angular momentum operator and some problems on spherical harmonics. So, first problem: consider a system of two non-interacting identical particles of mass m confined to a two-dimensional potential box of length L. So, find the energy and the wave function of the ground state of the system when the particles are A, fermion, B, bosons. Assume that both the particles are in the same spin states. Let us start. Let us assume that x1, y1 and x2, y2 are the two position space or of this spin system, of this interacting particle system. And to start with, now the wave function of this composite system of two particles will be psi m1 n1 m2 n2 as a function of x1 y1 x2 y2. Just recall, before we go to the finding the wave function and energy, recall for a particle in a box, particle in a box of length L, the wave function was given by, or rather time independent Schrodinger equation was given by minus h cross square upon 2m psi n x d square by dx square. This is the kinetic energy operator, plus if I consider a free particle, it will be just correct. Here n is the quantum number, x is the coordinate space. So, for one dimensional particle we just have the wave function as psi n x, which is 2 by L square root of 2 by L sin n pi x by L. Okay. And the energy, corresponding energy is given by n square pi square h cross square upon 2 m L square. Okay. So, psi n is the solution of this equation and E n is the corresponding energy. So, in the same line we have psi m1 n1 m2 n2 x1 x2 x1 y1 x2 y2 will be the wave function for the particle in a box, for two particles in a box in 2 dimension. So, the corresponding time independent Schrodinger equation will be minus h cross square upon 2m d square dou square by dou x square plus dou square by dou y square. We have x1 y1 for particle 1 plus x2 and y2 for particle 2 psi, that is equal to E psi. So, Schrodinger equation for two particles in 2 dimensional box. Here 1 indicate the first particle, 2 indicate the second particle, m and n represent the quantum numbers for particle 1 along x and y direction, for x and y direction. So, solution to the above equation can be written as the wave function. This is the wave function we had already written, but this can be rewritten as x1 y1 x2 y2 wave function of individual particle. So, phi n, phi m1 x1, phi m2 n1 y1, phi m2 x1, phi n2 x2, and this is y2. So, each of these wave function would correspond to these values. So, for first one phi m 1 x1, the wave function would be 2 square root of 2 by L sin m1 square pi square h cross square upon 2 m L square, and similarly the others would go. And the energy E m1 n1 m2 n2, I denote it by this subscript, will be equal to m1 square plus n1 square plus m2 square plus n2 square pi square h cross square upon 2 m L square. So, this is the energy energy of the composite system which has the wave function this. Okay. And remember that the wave function is of this form between the regions x less than 0, less than L greater than 0, that is inside the box. However, this wave function would be 0 for x less than 0 and x greater than L. This is the same condition which we have for the particle in a box. So, this in this case it is x and y both. So, this will be same for y also. This will be same for y also, x comma y. Okay. Now, for the case of fermion, you have seen in the lecture already. for the case of fermion, for fermions, the wave function would change in sign. So, for fermions the wave function should be antisymmetric or it should be like the odd function. So, for fermions wave function is antisymmetric. Under exchange of particle. So, when we exchange particle 1 with particle 2, we will have a additional minus sign. That is to say that the wave function is now written as psi minus. Minus indicates that the wave function is antisymmetric. The same notation I am using as it was used in the lecture. So, here I have psi m1 n1 m2 n2 minus psi m2 n2 m1 n1. Okay. So, when I exchange particle 2 by particle 1, when there is a flip, there is a change in sign, and this factor is the normalization factor. For boson, if the two particles are bosons, then the wave function is symmetric. So, when the wave function is symmetric, we represent it by a plus sign, m1 n1 m2 n2 will be square root of 2 psi m1 n1 m2 n2 plus psi m2 n2 m1 n1. So, if you interchange particle 1 by particle 2, there is no change in sign, it will remain symmetric. So, as a example, just for fermions, this is example you can try. For fermions, if a wave function psi minus 1 1 1 2 is given to you, then what would be the possible, what will be the possible energy? So, you calculate E 1 1 1 2, what do you get? And you can take one more example for bosons. If the composite system is of two bosons, then let me take same quantum numbers. What will be this? So, just try this. Let us go to the second problem, spherical harmonic. Second problem, you are given the spherical harmonic y00 and you have to find out whether y00 is a simultaneous eigenfunction of L square, Lx, Ly and Lz. What do I mean by this? You have to find out commutator of L0, y00, L square, y00, Lx, Ly and commutator of y00 with Lz. So, this you need to evaluate, which I think when you write this in the in polar coordinates or in terms of L square in terms of y, you can easily do this by just writing down the value of y00 and L square. You can either use ladder operator, you can write in terms of ladder operator if you wish, or you can just simply write the spherical harmonics and L square in polar coordinates and try to see what you get. So, this is for you exercise, you can try. Then going to the third problem, recall the definition of spherical harmonics which was discussed in the class. Okay. So, what is the definition? Psi L M theta phi, you can write this as n cap L M L, and using this definition or the notation, you have to find out what is y31 and y3 minus 1. What you are given is y30 as 7 by 16 pi 5 cos square theta minus 3 cos theta. This is given and you have to use the ladder operator. So, if I want to go from 30 when operated on L plus, we can obtain, right. Similarly, if I go from y30 to y3 minus 1. So, when the quantum number changes from 1 to minus 1 or 0 to 1 or 0 to minus 1, you will use ladder operator. So, this will give us 3 minus 1 theta phi. Using this, you have to obtain the result. So, we use these two. L plus on L ml would give us C plus, you get a Cleshko-Gordon coefficient for L plus, which will be, let me call it as C plus, and then you have N L m plus 1. So, when you do this, this is equivalent to writing L plus psi 3 0, where m is 0, L is 3, will become C plus, and here you have 3 plus 1, 0 plus 1, I get 1. So, I have to evaluate the value of C. So, for L is equal to 3, m is equal to 0, I will have C plus as square root of 12, and this will be as it is theta phi, theta phi, theta phi. So, y31 theta phi will be L plus, I will write in terms of 1 by 12 psi 30. L plus, I will write in polar coordinate as h cross e raised to I phi dou by dou theta plus I cot theta dou by dou phi. And when you operate this on y is nothing but 7 upon 16 pi 5 cos cube theta minus 3 cos theta. So, when I operate this on this function, this term will not contribute because this operated on this function will give me 0. This will give me 15 minus 15 cos square theta sin theta minus 3 sin theta. So, minus will become plus. Y 3 1 theta phi would be 7 by 64 in the square root, because here we had 16, then here you have square root of 12, 7, 16 pi. So, I will have here on simplification, I will get this derivative will be minus 15 cos square theta sin theta plus 3 sin theta. So, just check after simplification if you get this result 16 into 12. Okay. So, 3 I have taken out, this will be 16 1 by root 12. Here if I take 3 out, I will have 7 by 16 pi in the square root times, I have 3 outside. So, I have minus pi cos square theta sin theta plus sin theta. In fact, I can take sin theta also outside and then simplify it further. I can just take sin theta outside 1 by 12 and I have a 3 over here. Okay. So, this will result in 21 upon 64 pi sin theta minus pi cos square theta plus 1. In the same way, and see to it that you are carrying out this properly. Here I have e raised to I phi, which I was not writing throughout. So, I will just include it here, e raised to I phi, which has to be included everywhere. Similarly, y 3 minus 1 theta phi would be 21 square root of 21 64 pi e raised to minus I phi 1 minus phi cos square theta sin theta. Okay. So, this is the result you can check whether you obtain this. So, the crucial part here was that you write L plus in terms of the polar coordinate and then you operate this on the y 3 comma 0 given to you and then you can easily see the result. So, with these 3 problems we can discuss the remaining problem in the next part of the tutorial.